welcome to another edition of Topics in Physics. All right, so today what I hope to talk to you about has to do with vectors. Minute. We'll talk more about vectors and I'll talk to you about Newton's laws of motion. I'm sorry about this. Do you have any questions before I begin? No? Okay. So last week, I told you that in physics we have quantities that can be grouped as being either scalars or vectors, right? So what is the key difference between a vector quantity and a scalar quantity? Do you remember? So vector has both magnitude and direction, but a scalar has only a magnitude, right? So like, for example, velocity is a vector quantity, where speed is a scalar quantity. And we use arrows to represent vectors diagrammatically, graphically, right? So the length of the arrow coincides with the size of that vector, the magnitude, and how the arrow points is telling us the direction. And then I spoke to you about how if you have two vectors and you'd like to add them, like two displacement vectors, you can do so by the tip-to-tail method and or the parallelogram method, right? With the tip-to-tail method, if you have two successive displacements, one after the other, you can add to the tip of the first displacement, the first arrow, the tail of the second, and the resultant goes from the tail of the first to the tip of the second. And if the vectors form a right triangular configuration, it's not difficult to figure out the magnitude and direction of the resultant vector. The magnitude comes about from the Pythagorean theorem, and the direction you can figure out using a kind of inverse tangent operation. Okay, the parallelogram method is very similar. You take the two vectors, you connect their tails, and then you construct a parallelogram out of those two vectors as sides of it. And along the diagonal of that parallelogram, you have the resultant. Okay, so is that where we left off in class last time?
Yes.
Vector addition, right? Okay, so we can add displacement vectors. Okay. But there are other vectors that we can do the same kind of analysis with. So we can have force vectors. As well as velocity vectors. Right. A force is a push or a pull. And so imagine that there are two forces acting on an object, and we'd like to find the net force or the overall force, the resultant force, right? So let's say that on a sheet of ice, we have a hockey puck, okay? And then their force is exerted onto the hockey puck via the use of hockey sticks, right? So one force is directed to the right, and the other force is directed downward, okay? And the forces I will call F1 and F2, okay? And F1 is pointing east, F2 is pointing south, so this is a top view. Let's say F1 has a strength of 10 units. In physics, the SI unit of force is the Newton. So I can say 10 N, so N represents newtons, okay? And let's say F2 has a magnitude of 24 newtons, okay? And I can ask, what is the vector sum of these two forces? Or if you like, what is the resultant force? Like if you could reimagine the system with a single overall force acting on it, what would that force be? That force would be called the net force, and it's just the vector sum of F1 with F2. So, okay, so Brian, you cannot see the writing. Are all of you unable to see what I have on there? F1, F2,
I could see the writing.
you can?
Yeah.
So,
Yeah.
if you expand your window, if you expand the window, maybe then you could see everything. If not, let me know. Okay, I mean, I have a blackboard behind me. I could also write on the blackboard if that might be easier. I don't know, but I think this is fine. All right, so I want to know what is the net force, right? Acting on the hockey puck, and for that I want you to provide both the magnitude and the direction. Okay, so essentially what I'm saying is I want to add the force F1 with the force F2 to find the resultant force, or let me just call it the net force, okay? And I want to know what is that equal to, right? Well, which method would you like to employ to add these two vectors? What would you like to do?
Keep the tail.
Yes, let's do exactly that, right? So we'll connect to the tip of the first vector. Now, it doesn't matter where you place your vectors in space, so long as you don't reorient them or rescale them. So I'll put F1 over here. I'll connect to the tip of this one, the tail of the other. Okay, something like that. Sorry, and then the resultant lies from the tail of the first to the tip of the second. That would be the net force. And you could see a right triangular configuration, right? Where the length of F1 is 10 newtons, and that of F2 is 24 newtons. Can somebody tell me what is the magnitude of the net force? Well, if you subscribe to the Pythagorean theorem, this is just going to be the square root of the sum of F1 squared with the magnitude F2 squared, right? And in that regard, this is then the square root of 10 squared plus 24 squared, right? And that's going to give you 100 plus 24 squared. So that's 24 times, let me use the distributive property of math, 20 plus 4. I don't have a calculator handy, so I'll just multiply 24 by each term in the parentheses and add. So I have 480 plus, let's say, 696, 576, right? And if you add 576 to 100, you get 676. And if you take the square root, you find that the net force should be 26. Okay, if you work it out, it should be 26 newtons. That's the magnitude. 26 squared should be 676. I need a direction, so maybe I want to find this angle here. Right, so this angle would be south of east, okay, or below the positive x direction, if positive x is lying to the right. Okay. So can somebody tell me how to obtain the direction? How do I get the angle theta?
Would that be using the tangent?
Yeah, you can use tangent, right? So you can say the tangent of theta is opposite over adjacent. So in this case, f2 over f1. And so the tangent comes out to being equal to 24 over 10, which is just going to be 2.4, right? And then to find the angle itself, the angle is the inverse tangent of 2.4. And that you can use a calculator online to work out. Did I show you Wolfram Alpha, the program online that you can use to calculate angles?
Yes.
So you can use that, right? Also, you can use Wolfram Alpha to do various other things, right? Algebraic manipulations, compute various operations. But if I do this, if you want, I can share my desktop, but I think it should be okay, right? If you have questions, just let me know. If you go to Wolfram Alpha and you type in, just write the words inverse tangent of 2.4, the answer should pop up. And I get 67.38 degrees. So the answer. Theta is 67.38 degrees south of east, right? South of east, or below the positive x-axis. That's the direction. The magnitude was 26. Any questions about this one?
How do you determine the south of the
How did I determine the
south of east part?
south of the, oh, okay. Good. So looking from above, going to the right means east, right? So hold on. So meaning this is east, going up is north, left is west, down is south, right? I'm looking from above. So if you want, east is positive x, west is negative
Oh,
x.
got it.
So we're going east, but we're deflecting east southward by some angle, right? As opposed to going east of south, that would be this angle. So I could say the answer is 67.3 degrees south of east, or equally valid is to say if you take 90 degrees and subtract from that 67.38, you get 22.62. So that's 22.62 degrees, but that's east of south. So you're heading south, but then deflecting eastward by that. Either answer is correct. Okay.
Thank
So
you.
that, sorry, this angle, I shouldn't call theta. This angle I would call maybe phi, right? So that angle would be this angle here relative to the vertical, okay? Up there, as opposed to the horizontal. All right, so that means that the same object can be viewed as having just a single force acting on it. You draw it over here, where that force is acting like this, okay? That would be called the net force. It has a direction, 67.3 degrees south of east, and the magnitude of it is just 26 newtons, okay? Now, forces dictate accelerations. Like a force means that there will be an acceleration in general, okay? Meaning a rate of change of speed, a rate of change of velocity. And the greater that force, the greater the rate at which the speed is changing, it turns out. Okay. Any questions on that? Any more questions? No? No. Give me, can't seem to find the cursor for the mouse here. Okay, what's going on? All right, give me a minute, hold on. Apologize. All right, I got it. Okay. Sorry about that. Okay. Let me clear the page. All right. We can also understand vector addition through the lens of velocities. Okay. So let's talk about vector addition in the context of velocity, vectors of velocities. So imagine that there's an airplane, a fixed height above sea level, okay? And you're looking at things from the top. Okay? Let's say we have a top view. And so let's say, here's the airplane, okay? It's directed northward, okay? And there's a velocity here of the plane relative to the surrounding air. That's a vector. Okay, now any velocity that you can conceive of is a relative concept. It's in relation to some frame of reference, correct? Because right now, my velocity, one could argue, is zero. I'm not moving, but I'm not moving relative to you or relative to the Earth's surface. I am moving relative to the sun, right? Because the Earth is revolving around the sun, and I'm carrying the motion of the Earth with me. So I am moving relative to the sun, right? So whenever we say velocity or speed or acceleration, we mean with respect to some reference frame of reference. Usually it's the Earth's surface, ground, okay? Like if you say a car is moving at 50 miles per hour, it's understood that's relative to the Earth's surface. But sometimes that doesn't have to be the case, right? So my notation here, VPA, is to suggest that there's a velocity vector, and the velocity here is the velocity of the plane relative to the air, okay? But let's say the air itself is moving. Let's say there's wind. Okay, so imagine that there's wind blowing eastward, okay? And so there's a velocity there. So let's call this, I could say it's the velocity of the wind, right? But let me write it in this manner. This is VAG, okay? This will be the velocity of the air relative to the ground, okay? Relative, or to the air traffic control tower, relative to the ground, okay? This is the velocity of the wind, if you like. And let me give you the magnitudes of these velocities. So let's say the speed of the plane relative to the air is 300 kilometers per hour. I could use meters per second, I should, but let me just use kilometers per hour. That's okay. And let me also say that the speed of the air relative to the ground, the wind speed, if you'd like, is, I have 300 there. All right, actually, let me provide values that are more representative of what you might actually encounter in the real world. Right, so so the speed of the plane relative to the air, let's see. Okay. Some more people are coming into the session. All right. So I have an airplane, a fixed height above sea level. It's directed northward. There's a velocity of the plane relative to the air. That vector is north. And the speed of the plane relative to the air, the magnitude of that velocity is what a speedometer in the plane would measure. Okay. And I'm trying to give you a value for that. I just want to make the numbers work out nice. So let me think carefully. Right, so let's say this would be 400. Okay, let me use meters per second. Now that's about 800 miles per hour. That's fairly high. Okay, but nonetheless, let's take that to be true. Usually in flight, the speed would be more like 400 miles per hour. So like 200 meters per second or so. Let's also say that the speed of the air relative to the ground, that wind speed, is 300. That's fairly fast too, right? That's about 600 miles per hour. Let me just use these numbers. So then I can ask, okay, what is the resultant velocity? What is the velocity of the airplane relative to the ground? All right. So the plane is moving relative to the air, but the air itself is moving relative to the ground. Ergo, there must be a velocity that the plane exhibits relative to the ground. And it seems intuitive to say that the velocity of the plane relative to the ground, what we're seeking to determine, okay, this is our resultant velocity. That velocity of the plane relative to the ground is the velocity first of the plane relative to the surrounding air. Some more people are joining in. Okay. I'm sorry. I'm trying to get everything in order here. All right, so that all of you are able to follow along. So again, we're looking at a scenario by which there's an airplane at a fixed height above sea level, a fixed altitude, and the plane has a velocity relative to the air. Okay, that vector is directed northward, and the speed of the plane relative to the air, the magnitude of that velocity, is 400 meters per second. Okay. We have a crosswind that's blowing. So at the same time, there's wind blowing from the west eastward, right? So the direction of the wind is east, and the speed of the air relative to the ground, the speed of the wind, if you'd like, is 300 meters per second. So then the question I have is, what is the velocity of the same airplane, but relative to the ground? Because I want you to specify both the magnitude and direction, because velocity is a vector. So I claim that the velocity of the plane relative to the ground should be first the velocity of the plane relative to the surrounding air, plus the velocity of the air relative to the ground. Okay. All right, someone else is joining the session. All right. So then I'm just adding vectors, right? It's just like saying I'm taking two vectors A and B, right? Two vectors, and I'm adding them to get a resultant vector. Okay. So PG, my notation here, means plane relative to the ground. Right? So now, does this expression make sense? This is how relative velocities add together. Okay. Does this make sense to you? Yeah. Okay. So remember, I'm not adding magnitudes. I'm not saying at all that the speed of the plane relative to the ground is equal to the speed of the plane relative to the air plus the speed of the air relative to the ground. I am not saying that. Okay, that is not what I'm saying. That is not true, right? Because these vectors are not pointing in the same direction. They're perpendicular to each other, right? But I'm saying as a vector sum, this is a vector equation or a vector valued equation. That is true, right? But in terms of magnitudes, that's not true. Now, notice my notation. It's kind of interesting. If you look at the labels, the subscripts, right, of these velocity vectors, you notice that you'll have two subscripts for each velocity vector. And the inner labels here are A, right? But those inner labels don't appear on the opposite side, but the outer labels P and G appear, right? And it's true in general. If you have relative velocities, they add up in that way. So one can say the velocity of, let's say, the frame of reference A relative to the frame of reference C is equal to first the velocity of the frame of reference A with the frame of reference B, some intermediate frame, plus the velocity of the frame of reference B with respect to C. Okay, the inner labels cancel, the outer labels dictate the relative velocity that you're seeking. Okay. So then I'm just adding vectors. I'll use the tip to tail method again. I'll add the velocity of the air relative to the ground, which is pointing eastward. I'll add to the tip of it the velocity of the plane relative to the air, which is pointing northward. Right, and the resultant should lie from the tail of the first to the tip of the second. Let me show it in a different color. Resultant vector is in red. Okay, that's the velocity of the plane relative to the ground. And what that tells me is that if these velocities are constant, then the plane will drift in that direction in red, meaning the airplane, right, will drift like this. Okay, you're looking from above, it just drifts like that. It's intending to go directly north. Okay, it's intending to go there, but it drifts, and it might end up at some time over there. Right? It drifts in that direction. It keeps the same orientation, but it's drifting, right? With a speed that's larger than the speed of the plane relative to the air, because this is the hypotenuse of a right triangle. Right? Can somebody tell me what is the speed of the plane relative to the ground, the magnitude of that velocity? Or how I would go about finding it? So you're saying 700. Well, remember, it's the length of the hypotenuse of a right triangle, right? These two vectors, VAG, VP, are not coincident. They're not pointing along the same direction. They're not parallel. So I have to use the Pythagorean theorem, right? VAG, the speed of the air relative to the ground, is 300. Whereas the speed of the plane relative to the air is 400. Right? And I have a right triangle. So that means that the speed of the plane relative to the ground is the square root of the sum of those side lengths squared, right? VAG squared added to that VPA squared. So the plane speed relative to the ground is the square root of 300 squared plus 400 squared. Okay. And if you work this out, it's a scaled up version of a 3, 4, 5 right triangle. You scale it up by a factor of 100. You should get the answer to be, you can check with the calculator, it should be 500 meters per second. 500 meters per second. It should be the speed of the plane relative to the ground. So what I'm saying is that the plane drifts in that oblique direction with a speed of 500 meters per second. The wind is helping it gain a speed, right? Let's see, there's some questions on the chat. Okay, if if there was not a this is called a crosswind. Okay, what I have here, crosswind. If let's say I had a tailwind, okay, what does that mean? Let's say the wind is pointing east, okay, but the plane is oriented east as well. So imagine this is the plane, it's going like this, okay. So this is the velocity of the plane relative to the air eastward, okay, and the velocity of the air relative to the ground eastward, right? If I then want to know what is the velocity of the plane relative to the ground, well, the magnitude is found by simply adding up the sum of the magnitudes of the speed of the air relative to the ground with that of the speed of the plane relative to the air. In this case, it would be 700. Okay, only in this case, that's if you have what I call a tailwind. Okay. If you have a headwind, like imagine that up here, okay, the plane is heading this way, west, okay? The speed of the plane relative to the air is the same, let's say 400, but it's heading west. And there's a wind blowing in the anti-parallel direction, right, to the right, eastward, because that's the wind. So this would be a headwind, if you'd like. You're going against the direction of the wind, right? So your velocity is going to be reduced. Can somebody tell me what is the speed of the plane relative to the ground here in this scenario? So you're going east, rather west, at 400 meters per second. The wind is blowing east at 300. What's the net speed? What is the speed of the plane relative to the ground? 100 is correct, okay? And that is directed to the left, right? Westward. So the velocity of the plane relative to the ground in this example is directed purely to the west. Okay? In the case of the tailwind, that velocity vector, as you can see, is directed eastward. In the case of the crosswind, that velocity vector is directed at some angle which we have yet to determine, theta. Okay, that's north of east. I should say that the analysis here for velocities works the same with displacements and forces. Like if I had two forces perpendicular, the net force is in an oblique direction. If two forces act on an object, right, in the same direction, then the net force is found by just summing up those two. Always true, but the magnitude of the net force is found by summing up the magnitudes of those two forces. If you have two forces acting anti-parallel, one pushing one, let's say one or maybe two pushes on a block on a tabletop that's frictionless and smooth, and there's a force acting one way, let's say to the east, and a force acting another way to the west, and the one to the east is 400 newtons in strength, and the other to the west is 300 newtons pointing westward. The net force is in the direction of the larger of the two, right? So the net force would be 100 pointing east. Okay, so but it's the same analysis. You're just adding vectors. You take the difference in magnitudes there, larger minus smaller, winning force minus losing force. So we found that in our example with the crosswind, the speed of the plane relative to the ground is 500, but we have to also figure out the direction, right? The velocity of the plane relative to the ground has that magnitude, that speed. But what is that angle theta? Can anybody figure out or tell me how to get theta? I can use tangent, right? So I can say over here, the tangent of theta is opposite, which is VPA over adjacent, VAG. And so the tangent of theta is going to be 300 over 400, or 3/4 if you'd like, so that the angle itself is the inverse tangent of 3 over 4. And if you put that into a calculator, if somebody can check, you should get 36.9 degrees. This is 36.9 degrees north of east. Okay, that's the direction of the plane's velocity relative to the ground. So what I'm trying to tell you is that if there's an airplane moving at a constant speed relative to the air of 400 meters per second directed northward, and there's a constant wind blowing at a speed of 300 meters per second east, what you find from the vantage point of the ground, okay, is the plane is drifting at an angle of 36.9 degrees north of east at that angle, okay, with a speed that's actually larger than the speed of the plane relative to the air. That speed is 500 meters per second. Is this okay? Is that all right?
Yes.
Yeah, okay. Is it okay with you if we take a 10-minute break right now? Can we take a bit of a break?
Sure.
Okay, let's take a break and then 10 minutes, okay? Okay. So we've been considering vector addition in the context of displacements, forces, and velocities. We said that a velocity is really a relative concept. It's relative to some frame of reference, right? It's not an absolute concept. So if my velocity is 0 right now, you would say it's 0 relative to you, but it's not 0 relative to the sun. And then one can ask, like, is there anything really absolute in the universe, in our everyday lives, right? Like there are moral truths that are absolute, like an absolute moral truth. Like you say, thou shalt not steal, right? So stealing is a sin, or it's the wrong thing to do. But let's say there's an individual who has reached hard times and needs to feed his family members. Maybe he needs to feed a child of his, and he's at a bakery and doesn't have enough money to buy a loaf of bread, and so decides to then steal the loaf of bread. Well, is that morally justifiable? So there are these interesting ideas, right? So relativism and absolutism, right? While velocity is relative, right? It seems that one particular velocity or kind of velocities is absolute. So it turns out if there's a passing beam of light, no matter what the state of motion is of the observer measuring the speed of that beam of light, the observer will always say that it's the same speed, c. C is the letter that we use to denote the speed of light in vacuum. That number is 3 times 10 to the 8 meters per second. Okay, so c represents the speed of light in vacuum, and it's about the same as in air, okay, a bit less in air, but that number is 300 million meters per second, about 700 million miles per hour. Okay, 700 million miles per hour. It's an extremely large speed, but let me write it out. So let's say 300 million meters per second, right? In power of 10 notation, we can write this as 3 times 10 to the 8 meters per second. Now, I said that whenever there's a beam of light passing along, if there's an observer that's trying to measure the speed of that passing beam, that observer will always measure the same speed, which is very counterintuitive, right? But nonetheless is in keeping with experiment, what we find through observation. So this is a kind of experimental fact, right? So no matter what the state of motion is for an observer, he, she will always measure the speed of a passing beam of light to be that value c, okay? Now, this is non-intuitive, okay? This is not in keeping with your intuition, with what you would expect. Let me explain, right? Now, because this is experimentally verifiable, this is observed, right? There's a deep consequence of this, right? This is getting to the heart of of space and time, right? So this suggests that time is not absolute, okay? That's counterintuitive in its own right, that time doesn't tick the same for everyone, okay? So this is an implication. And another implication is, when we were here, okay, is that the lengths of objects are not fixed in stone. And like if I have a marker and I'm holding it, okay, I measure a certain length, but if I'm moving in a train with the marker, okay, and you measure that speed, rather that length of the marker from outside the train, you'll find that the length is not the same, right? So this suggests that the lengths of objects, okay, are not absolute, they're relative, okay, like time. So these two boxed-in statements are also, they themselves are non-intuitive, okay? So this idea of the speed of light always being the same, no matter what the state of motion is for the observer, is like a hallmark principle that's in Einstein's relativity theory, the special theory. We call it a relativity, okay? Now, I'm just going to speak a bit about this, but I'm not going to test you on it, okay? But I think it's kind of cool, right? So this was developed by Albert Einstein. Okay, so again, I'm not going to test you on this, but I think you should be exposed to it at least once, you know, if you haven't been exposed to it before, okay? So you see how it works. So I said, the idea that a passing beam of light will always be measured to have the same speed is non-intuitive. All right, so let me show you, okay? All right. Can I erase this? Why not? Okay. Here. First, let me pose a question to you, all right? Let's say there's a car here, okay, moving along the road at a speed of 50 meters per second, okay? Now let's say that you're running along, okay, the road, okay, and you're running at a speed of, let's say, 10 meters per second. Okay, so this is the car, and that's you, okay? You're moving in the same direction as the car, but with less of a speed. So now I ask you this, what is the speed of the car relative to you? What would you argue? What does your intuition say? If you are standing still, okay, if you're standing still, then the speed you would measure for the car would be the same that the ground would measure, that the Earth's surface would measure, right? Because you're one with the ground. You're not moving with the ground, so that would be 50. But you are moving relative to the ground. So Brian says 40. That's correct, right? So you're sort of killing off some of the motion of the car by you moving at 10, right? So the car relative to you is not moving as much. It's moving at a reduced speed. The speed is reduced by the speed with which you're moving along. So I would say that the speed of the car relative to you is reduced by the speed with which you're moving. So it's 50 minus 10, and that's 40. And that velocity, by the way, is directed rightward, okay, as a velocity. Okay? Velocity of the car relative to you. Let me write it this way, maybe the velocity of the car relative to you, or something like that, okay? Very good. Right, now, here's another example. This is where it gets tricky, okay? Let's say I'm here. That's me, okay? You can think of me as the ground if you'd like. I'm just standing at the ground somewhere. So I'm not moving relative to the ground. If you want, think of me as the ground. I have a laser pointer, okay? I shine a beam of laser light across the room. So here's light, okay? And it moves at speed c, right? Relative to me, relative to the ground. But let's say you're running, okay? This is you, and you're running. This is you, but you're not running at 10 meters per second. Let's say you're running at a high speed. Let's say you're running at 3/4 the speed of light, okay? 3/4 the speed of light. So I ask the question now, what is the speed of light, the beam of light, not relative to me, but relative to you? Okay. So, to answer this question, so I expect, right? I expect you to tell me, right, that light is traveling at, you fill in the blank, right? At what speed relative to you? What's the natural expectation? You're moving at 3/4 c. The beam of light is moving at c, right? So you're catching up to it. You're killing off part of its motion. Right, the expectation is it should be c minus 3/4 c, right? But c itself is 4/4 c, so this should be 1/4 c. Right, and you would have, I expect you to make this measurement based on dividing distance over time, like the length covered by the beam and the time to go from where the beam leaves the laser to where it hits a wall or something, okay, to cover that length. Distance over time, I expect you to get 1/4 c, but, okay, what's interesting is that you tell me that, and this is why it's contradictory, that the beam of light is actually moving at the same speed with which I'm measuring, of which I'm measuring light, right? Is that actually moving at c, right? Exclamation point. This is where it's non-intuitive, this statement right here. You tell me that it's actually c. So then because of this, I accuse you of using slow moving clocks. Okay, I'll explain. So then because of that, I say to you, right, I accuse you of using a slow clock. Right, let me explain why. Let me erase the top. Meaning I'm saying that your clock is running slower than mine. Okay, let me explain why that's true. In fact, let me assert the following. So what I'm saying is the following. I say that when 1 second has passed for me, okay, 1/4 of a second has passed for you. That's what I'm saying is happening. Right? So your clock is moving slower than ticking slower than compared to mine. Has passed for you. Why is that? Why am I saying that? Okay, so let's think about it this way. Very, very simple. Okay. I expect you to get 1/4 c. Okay. But you tell me that the speed of that beam of light relative to you is not that it's c. Okay. So I want to ask everyone the following. How do I go from 1/4 c to c? What mathematically, how do I go from 1/4 to 1? I'm just gonna get my coffee. Just think about it. How do you go from 1/4 c to c mathematically?
By squaring it.
No, I'm saying how do you go from 1/4 to 1? You multiply by 4. That's good. So meaning you just have to multiply by 4. So this is what's really happening. You see, speed is distance over time, right? That is speed, essentially, right? So I'm saying that your time, right, is slowed down compared to mine, meaning that if I measure 1 second, then it's 1/4 of a second for you. So basically, this time is divided out by 4, right? And if you notice, then that 4 comes upstairs, right? So then this would be 4 times d over t. And that's like saying you're multiplying by that factor of 4, right? 4 times c, right? Sorry. So what I'm saying is it works if your clock is slowing down. So if 1 second passes for me, 1/4 of a second passes for you, then that's where that scaled up number of 4 is coming in. So it's increasing what I expected you to say by a factor of 4, and that's why you're telling me it's C. Do you understand what I just did there? Is that okay? Or no? Let me try, because I'm trying to say it's counterintuitive, right? When you tell me that the speed of that passing beam of light is c, because you're moving at 3/4 c, I expect you to tell me that it's less than c by the amount by which you're moving, right? C minus 3/4 c is 1/4 c, but you're telling me c. So I'm saying that your clock is running slower compared to mine, in the sense that if 1 second passes for me, just 1/4 of a second passes for you. And that makes sense because to go from 1/4 c, the expectation, to the observed speed c, there's a factor of 4 being multiplied here, right? Where is that coming? See, if the speed is distance over time, but the time is reduced by 4, yeah, let's say it's 1/4 as much, then if you divide by 4, like when you divide by a fraction, you multiply by the reciprocal, the 4 comes upstairs. That 4 is what you're multiplying this by to get the c that you're telling me. Is that okay? Meaning, if it helps, this d over t, this should be equal to what I expect, 1/4 c, okay? What I expect you to tell me. Right, so I expect that should be equal to 1/4 c, but it's not. You're getting c, so that there's a factor of 4 multiplying this, and that's where it's coming in. Is that okay?
Yes.
Okay. So if you want, if this is the time for me, the time for you is not the same. The time for you is basically 1/4 the time for me, meaning, okay, so I'm going to be a bit more, maybe this is overkill, but I'm saying there's a time that I'm measuring, right? Like, for example, let's say 1 second, okay? And there's a time that you're measuring in relation, that would be 1/4 of a second, right? So that's basically the time for me divided by 4, right? So if it helps you, if I work it out that way, you can see why the speed of light is being the speed that I expect you to tell me for light is being multiplied by 4, right? I hope this is okay. This thing here, if you want, is 1/4 c, right? Okay, then, so what are we saying, right? We're saying that, you are running and I'm stationary. So then what we're saying is, so the implication, the philosophical implication is this, that moving clocks that are in motion, okay? Moving clocks run slower. This is a direct consequence, right? So if a clock is moving, like you're carrying a clock, you have to carry a clock with you and a ruler to measure the speed, right? But that clock then is moving and it's running slower than if it were not moving, right? So furthermore, okay, let's say you are moving not at 3/4 the speed of light, but 4/5 the speed of light, okay? 4/5, right? So let's say if I change up the numbers for a moment, okay? So let's say this is me again. I shine the beam of light across the length of the room, and now you're running, okay? But you're running at not 75% the speed of light like before, but 80%, let's say 4/5 c, okay? And you still tell me, right, that you're measuring c. Now, I expect you to tell me here, well, can somebody tell me, what do I expect you to tell me? Is the speed of that beam of light? I expect you to say that the speed is What is C minus 4/5 or 5/5 minus 4/5?
1/5.
Good, excellent, okay. But you tell me it's C, okay? So then now notice the following. We're going from 1/5 C, what I expect you to tell me, but you're telling me C. So now it's a multiplication of 5, right? So now I say that when 1 second has passed for me, 1/5 of a second has passed for you, right? Time has slowed down by more so than before. Remember, before when you're moving at 3/4 C, when 1 second passed for me, 1/4 of a second passed for you, right? Now I'm saying when you're moving at 4/5 C, I'm trying to make the argument that when 1 second has passed for me, 1/5 of a second has passed for you, right? Even less, right? So this is suggesting, so this observation then suggests that the faster a clock is moving through space, okay? Moving through space. And I don't mean necessarily outer space, okay, just anywhere in the universe. The slower time will tick. Okay. But you won't know unless you confer with somebody else. Like if you're running along very fast, right? Your clock is running slow compared to a clock that's not moving. And the faster you're moving, the greater the time dilation, the slowing down of time, right? But you wouldn't know unless you confer with me, unless you communicate with me, you won't know. For you, time is ticking ordinarily, right? You don't know any, we have to make a comparison in order for this to be realized, right? So you're moving and I'm staying still. Time is ticking ordinarily for you, it's ticking ordinarily for me. But when we talk to each other, when we compare our clocks, we see a difference, right? Then so moving clocks tick more slowly than stationary ones. Furthermore, the faster the clock is moving, the slower that time will tick, but you wouldn't know unless you confer with someone else. This means that time is not, the passage of time is not absolute. It's relative, it's a relative concept. It depends on your state of motion. The faster you move, the slower time will tick for you, but you won't know unless you talk to somebody else. Now you might say, hogwash, poppycock, this is not true. How do we know that this is the case, right? I think I mentioned it to you, but you can Google this, okay? So you might say, has this been verified, okay? Yes, it has. Let me explain. Let's see. So just to get a holistic picture, okay, I'm trying to say that no matter what the state of motion is for a passing beam of light, that observer will always measure the same speed for it, c, okay, 300 million meters per second. The example I gave was, I shine laser light, I'm just standing, so I'm not moving relative to the ground. You can say I am the ground, right? You're running along at 3/4 the speed of light. I expect you to measure the speed of light to be equal to a speed less than what I measure, less by the amount you're moving. So I expect you to tell me 1/4 c. And I'm alarmed to find that when you tell me what the speed is, you say it's c. So that number means that it's 4 times larger than what I expected. So I say, oh, I got it. Your clocks are running are running slowly compared to mine. So that when 1 second elapses for my clock, just 1/4 of a second elapses for yours. And that would explain why there's a factor of 4 being multiplied by what I expect so that you get C, right? So I say that your clock, your moving clock is running more slowly than mine, right? Then I said, what if you're running faster? What if you're running at 4/5 the speed of light? That's like 80% the speed of light instead of 75%, right? Then I expect you to tell me that the speed of the passing beam of light should be 1/5 c, right? It should be 1/5, but you tell me again it's c. So now from 1/5 to 1 or 1/5 c to c, it's a multiplicative factor of 5, right? 5. So that means then that when 1 second has passed for me, I'm claiming that 1/5 of a second has passed for you, even the slower amount of time than before, right? 1/5 is less than 1/4. And so you find that the faster a clock is moving, meaning in motion, like with the speed, right? Because you're carrying a clock with you to measure these times and a ruler as well to measure distances. The faster a clock is moving, the slower the time it will tick, the time it will register, okay? So the faster the motion through space, the slower the passage of time for that clock, but the person holding that clock would not know as such unless he or she confers with somebody else, like confers with me, okay? And so moving clocks tick slowly. The faster the motion of the clock, the slower the time will tick, okay? And so that means that time is not relative. It depends on the state of motion. Time does. The passage of time depends on the state of motion. The speed of a beam of light does not depend on the state of motion of an observer, okay? So the verification of this lies in the following scenario. Where is it? Okay. So I think I might have mentioned this. To verify that there is this notion of time dilation, that means a slowing down of time, that's based on motion, right? Based on motion through space. And again, the faster the motion, the slower time will tick. Okay, but again, you won't know unless you talk to someone else. Motion through space, anywhere in the universe. So if, let's say there's a jet airplane, okay? And there are two clocks that are synchronized to begin with. Let's call them clocks A and B, okay? Then one is placed in the airplane and one is being held by an individual, let's say me, okay? And you're in the plane. Now let's say the plane goes off to some exotic land, Hawaii or something, okay? Returns, right? Then we compare the times elapsed across both clocks. You find, okay, that less time has passed in the plane-bound clock, that's clock A, than in the earth-bound clock, clock B, right? So if there's a time TA, that's the time as measured by clock A, the plane-bound clock, and there's a time TB, that's the time measured by the earth-bound clock by me, right? The clock I carry. Which time should be larger? Which
Would it
time
be
should
the earthbound?
Earth? Yeah, that's correct. That is correct, right? So the time for the plane-bound clock is less. It's ticking less, right? Now this was observed. They took engineers and scientists, a team of these individuals took very precise clocks called atomic clocks, okay? And they synchronized them to begin with. So an atomic clock is based on what's happening at the level of an atom. So in a sense, an atom oscillates, okay? Per second, it oscillates millions and millions of times, right? A certain number. Let's say it's 9,630,000 times or something, okay? And it's so precise that that number that I just mentioned, 930 million and so on, okay, will not change for maybe centuries, right? And then maybe it changes in the ones place by one digit, okay? So it's very accurate, right? So it keeps time very well. So these clocks were synchronized. One was placed in a jet airplane, the other was left on the Earth's surface, and something like this happened. And they found that upon arrival, return, the plane-bound clock ticks slower, showed a less elapsed time than the Earth-bound clock. Now that difference, if you'd like, is very small. If you take the difference between TB and TA, right? That's like a fraction of a second. That delta T is very small. Okay, but it was measurable. It could be detected, right? Moreover, if the average speed of that airplane upon its flight was greater than before, then this difference in time is more pronounced. Okay, it's larger. So there's something called the twin paradox. So imagine that's me, okay, on the Earth, but I have a twin brother, okay? So same example, but my twin is in the plane, okay? One can do a calculation where you can ask, what should the average speed of this plane be where my twin is, right? So that, let's say, my twin, upon coming back to Earth, has aged only 10 years, okay? Where I have maybe aged 100 years. Maybe I'm no longer here, okay? So what I'm saying is that there exists such an average speed, let me just call it V bar, of this plane, okay? So that the time as measured by my twin, let's say, might be something like 10 years. So when my twin arrives, right, comes back, 10 years have passed for him, but he won't see me anymore because maybe 120 years have passed for me. And I live to be about 80 something or so, and I'm no longer there. So my twin returns, he's saddened to find that I'm not there. In a sense, my twin has traveled into the future. I hope you understand that. He didn't travel 10 years into the future. He traveled 120 years into the future, right? What's more is the faster that average speed, the greater the traveling into the future, right? So maybe instead of 120 years elapsing for the earthbound clock, 1,000,000 years can elapse. There's a scenario where that could be true, but the speed would have to be appreciably high, like very close to the speed of light, okay? If you can go at this very high speed, that's very difficult to attain engineering wise, and you come back, it's possible that 1,000,000 years have passed on Earth. That is, the Earth that you knew before you left is no longer that same Earth. Maybe there are aliens crawling about, there are no more humans, okay, but maybe 5 years just passed for you, but 1,000,000 years on Earth. Right? So in that sense, you've traveled into the future, not into the past, but into the future. These are interesting consequences to think about. All right. So sit with that for a moment. Is it okay if we take another 10-minute break?
That's fine.
Thank you. All right, let's take another break. Thanks, guys. So we'll continue. All right, so what I just mentioned about the speed of light and time dilation, that's interesting. I'm not going to test you on that. There's a lot more to say about this, but let's move on, okay? So then what I'd like to talk to you about next is a framework that was developed by a man who contributed more to science, I would say, than even Einstein, okay? Isaac Newton. Or Sir Isaac Newton, he was knighted. So he lived between the years of 1642 to 1727. He lived to be about 85 years of age. Right? He didn't know his father. His father died before he was born. He was very obsessive in whatever he was interested in. He would seek to understand things in a very fundamental way. So he was trying to, as he put it, understand the mind of God and understand the heavens and why planets move the way in which they did. And to understand the motions of planets, he had to understand the nature of gravity, because gravity is what holds a planet in orbit about the sun. And in order to understand gravity very well and fully, he had to develop calculus, right? So he's credited with the advent of calculus. That's the mathematics of change. So I'm not going to test you on any calculus, but it's at the heart of understanding motion, okay? There's always motion in the universe, motions of planets, motions of cars, motions of pebbles that are moving in ponds and so on. And to describe motion as a function of time, you need the language of calculus, right? Or the blood flow through veins and arteries in your body, okay? So he did that, and then with that, he was able to extract the law of gravity. It's called the universal law of gravitation. We'll talk about it, okay? And it came out as a kind of consequence of solving his equations of motion. And to solve, of course, you need ideas from calculus. He did some work in optics, in the study of the nature of light. Okay, but what we're going to focus on are his laws of motion, for which there are three. Okay, I'll talk to you about two of them today, and possibly the third as well. I have to see. Okay. All right. So these laws of motion, I'm going to give names to. Okay. There's the first law of motion, the second law of motion, the third. Okay. And if I can name them, the first one I'll call the law of inertia. The second one I'll call the law of cause and effect. And the third one I'll call the law of action and reaction. Now I should say that these laws cannot be deduced from anything simpler. Okay, they are postulates, if you like, axioms. You take them to be true, and if you do, you work out the consequences borne out, and you find the consequences agree with experimental observations, right? So if you, for example, use the second law to predict the acceleration of an object, and you measure the acceleration in the lab, you find that there's agreement. So that's why we have reason to believe that these laws hold true, okay? But they hold true in a certain regime. So I should say that what is the range of applicability of these laws? They don't work for all length scales, for all speeds. It turns out that if you want to understand the dynamics or motions of very fast moving objects moving at a speed comparable to that of light, you cannot use Newton's laws of motion. No, you cannot make useful predictions. You have to use relativity theory, okay? So I'll just say that these laws apply for objects moving at speeds, okay, that are much less than the speed of light, okay? Like the ordinary speeds that we deal with, the speed of a car, even the speed of a planet, but nothing like 80% the speed of light, 90% the speed of light. Okay? Also, in terms of length scales, if you want to understand the motions of objects that are very, very, very small in size, right, like atoms or subatomic particles, protons, electrons, you can't use these laws of motion to do that, right? For small length scales, for objects of atomic dimension in size or smaller, a new physics has to be used to understand what's going on, right? That physics is called quantum mechanics or quantum physics. So I'll just say in terms of the length scales, right? That we're looking at, we're saying length scales much greater in size than that of an atomic diameter, okay, the diameter of an atom, the size of an atom. For very small length scales, you have to use quantum physics. For very fast speeds, high speeds, you have to use relativity theory. You could say you could have an object that's small, moving awfully fast, like in a particle accelerator, where you shine maybe protons to a hard target. The protons move at very, very high speeds, 99% speed of light, and they're very small. So there you need quantum mechanics and relativity theory. And that's called quantum field theory, which we're not going to discuss at all. So here what we're looking at are objects of like macroscopic size, like baseballs, cars, planets, okay? And them moving not at such high speeds, right? And we're trying to understand their dynamics, and we'll use these laws to do so. Okay? Now, I'm not going to go in the order in which these laws are stated, but in order of increasing complexity. So the simplest one, I think, to understand is the third one. So let's look at that first, okay? So the law of action and reaction. So this states that for every action, there exists an equal but opposite reaction. What does that mean? Okay. So if you consider a wall, right, and I press my hand against it, right, I exert a force on the wall. I push on the wall. So that's the action, right? So there's going to be a force on the wall due to my hand. Okay, so this force is on the wall due to my hand, right? And I will call that the action. Okay. But Newton says that for every action, there exists an equal and opposite reaction. What he means by that is there's going to be an equal magnitude reaction and opposite in terms of direction. So the reaction is a force that's going to exist on my hand due to the wall. So this I would say is FHW. Okay, this is the force on the hand, due to the wall. Right? And that force has the same magnitude as the force on the wall due to the hand, this reaction force, okay, has the same magnitude as the action, but is pointing in the opposite direction. So we say equal magnitude, but opposite in direction, okay? If you want me to write an equation that relates the two, as vectors, they're not the same. One is the negation of the other, right? So the force on the wall due to the hand is the negative of the force on the hand due to the wall. They have the same magnitudes, but they're not the same vector because they point in opposite directions, okay? They don't have the same direction, but the magnitudes are the same. Essentially, the third law is telling you that you cannot touch something without being touched back, right? If you hit against something, that thing is going to hit against you in the opposite direction with the same strength. That's why if you consider a boxer, he wears gloves because when he throws a punch and he strikes an individual, there's a reaction force on the glove, right? So imagine a boxer didn't have a glove, right? So hits somebody in the face, then there's an action, and the reaction is a force back on the person's hand, right, on the bones, and that force of impact can be large, and it could crush the bones, right? It could hurt the person's hand. So you cushion the blow by wearing a boxing glove, right? Right. It turns out that because of this third law, we find that no force exists in isolation. So there are consequence of the third law is to say that no force exists in isolation. Meaning that if you approach me and tell me, Professor, I've discovered a new force, right? I can say immediately that there exists another force of the same magnitude pointing in the opposite direction. You can't have a force existing in and of itself, right? So whenever there's an interaction between particles, between objects, one exerts a force on the other and the other on the one simultaneously with equal magnitude but opposite in direction. Right? So if, let's say, I'm in deep outer space, okay, far away from any planet, any star that can influence me gravitationally. If I like move my hand, right, I'm not exerting a force on anything, it's vacuum, okay? So there's no force and there's nothing felt against my hand, right? So the minute you apply a force on something, right, then that something exerts a force back on you of the same strength but pointing in the opposite direction. Forces come in pairs, right? Whenever there's an interaction between me and the wall or between the earth and an apple that's falling towards it, even there, right, with the earth and the apple, the apple feels a gravitational pull from the earth. The earth exerts a gravitational pull on the earth. But by the same token, from Newton's third law, turns out that the apple produces a tug on the earth towards it, okay? yeah, the apple exerts a force of gravitation, force of gravity on the earth, but you don't see the earth rising to meet a falling apple, right? The reason being is while the forces are the same in magnitude, the extent to which the speeds pick up, like the accelerations, are vastly different. That is dictated not just by the force, which in this case is the same in strength, but by the mass, right? And because the apple has much less mass than the earth, the acceleration of the apple is more realizable, right? Able to be discerned more readily than the acceleration of the earth towards the apple. The acceleration of the earth is imperceptible, it's very small. Also, from the third law, you find that a pair of forces that constitute an action-reaction pair, right, do not act on the same body. So forces that form an action-reaction pair do not act on the same object, on the same body. Like if you consider that example with the wall, one of those forces, the action, right, is a force on the wall. That's a force on the wall. The reaction is a force on the hand. Notice those forces don't act on the same object. One is acting on the wall and the other is acting on the hand. Okay. In fact, in more general terms, you could say the force on object one due to object two is always the negative of the force on object two due to object one. Okay. They don't act on the same object. This acts on object one, and this acts on object two. Okay. And the forces don't have to be observed by your sense of sight. But you know of the effects based on acceleration. So for example, with gravity, like an apple falling, you can't see the earth pulling on it, but you know that there is something because as the apple is accelerating. Okay, so there must be forces produce accelerations, it turns out. Or electromagnetic interactions. If you have two metal spheres and you've charged them up by rubbing them against like a wool sweater, electrically charge them up, right? And you bring them close to each other and you let go, they repel. There's nothing pushing, there's seemingly nothing pushing them away from each other, right? It's not a visible force, but it's there nonetheless because you see things flying out. You see the acceleration in opposite directions. So some forces are not tangible, but nonetheless exist because we know the effects that they have on bodies. They accelerate bodies. Okay? And some forces are realizable, it can be observed like my hand pushing against a box on the floor or something or the other and allowing the box to slide across the floor. Okay. Applications of the third law. Well, let's consider, for example, swimming, right? You go into a pool, take your arms, you move them, you displace the water one way, you exert a force on the water due to your arms, right? That's the action. The reaction is the water exerting a force back on your arms at the same strength in the opposite direction. And that allows you to move yourself forward, right, in the water. If you consider a bird, right, a bird has wings and the bird displaces air with its wings downward. So there's a force on the air due to the wings of the bird downward. That's the action. The reaction is the air exerting a force back on the wings up, and that's how the bird achieves lift, right, and flies about. And there are many other examples you can think of. Rocket propulsion, right? So with a rocket, you have liquid fuel. The liquid is being burned, and it's converting, the liquid is then converting itself into a gas, okay? And eventually you have these hot gases that are going to be expelled out by the rocket. So the rocket exerts a force on the gas, expelling it out of the rocket. Okay, there's a force on the gas due to the rocket. That's the action. The reaction is a force from the gas back onto the rocket, same strength, opposite direction, allowing propulsion to take place, rocket propulsion, right? So the rocket then accelerates in the forward manner. It's similar to what happens with a balloon. Like if you blow air into a balloon, the volume of the balloon expands and then you let the air seep out, right? You have an opening there, you let the air escape. the skin of the balloon exerts a force on the air, driving it out. That's the action. The reaction is the air exerting a force on the balloon, the forwards manner, allowing it to propel itself forward. With the rocket, it turns out that the rate at which you burn fuel, the rate at which you convert the liquid to gas, is related to the acceleration of that rocket, the rate at which the speed is increasing. Meaning to say that the greater the rate at which you burn fuel, the greater the acceleration, the greater the rate of change of speed, right? That's what we find. But again, it's happening, the propulsion is really happening because of the reaction force. There was a scare in that in the early 20th century with the idea of rockets being developed and them going into space, that if, let's say, a rocket stops burning fuel in outer space, the worry was that it would fall back down to Earth because there's no air to push against it. In other words, it was believed that as a rocket is moving along, the air from the front of the rocket is displaced backwards, and then the air from behind is pushing on the rocket, propelling it forward, okay? But if you're in outer space, there's no air to do that, to give this kind of push forward. So there was a worry, right? But we know that that doesn't matter because even if the rocket stops burning fuel, and there's no third law here to worry about, you'll see in the first law, an object in motion tends to stay in that motion. So if the rocket is moving at the moment when the fuel has stopped being burned, it'll keep that motion. It'll keep that same speed and direction of travel unless there's a net force acting. It'll just move by its own volition, by its own natural tendency. It just will keep moving. And that wasn't always known, at least not for about 2,000 years, from the time of Aristotle to the time of Galileo Galilei, who preceded Newton's work. He lived in the century earlier, you could say. I think Galileo died the same year Newton was born. Yeah, that's 1642. Okay. I hope this is okay with you. Any questions about the third law? No? Okay. Let me consider the first law, okay? So I called it the law of inertia. I'll explain why that term is used in a bit, okay? So let me write this out, okay? So we say that an object in motion, oh, I should say, let me start by saying, sorry. An object at rest remains at rest unless an unbalanced, also known as net, force, push or pull, acts on it, okay? Now that's one part to it, there's another, okay? So for example, let's say on a sheet of ice, you place a hockey puck, okay? Gently there, and it just stays there, right? It stays at rest. There's no force acting on it. Well, there are forces acting. It's just that they balance each other out. What are the forces? So there's gravity tugging down, okay? But the ice exerts a kind of support force to prevent the puck from falling through. So there's a kind of support force, okay? In physics, we call it a normal force. Normal in math means perpendicular. This normal force, okay, is perpendicular to the surface here, the area of contact between the puck and the ice. Okay, it's perpendicular to that area of contact, and hence we say normal. No one of these forces is greater than the other, because if the normal force were larger than gravity, okay, the hockey puck would accelerate upward. If gravity were larger then the normal force, the hockey puck would sink downward, would accelerate down, but you don't see that, okay? So there is no net force, and so long as there's no net force, the object will continue to do what it was already doing, not moving, it stays not moving, right? Here's a question for you. Think about it carefully. Do the normal force and gravity here constitute an action-reaction pair? According to the third law, does gravity and the normal force constitute an action-reaction pair? So someone says yes. Actually, it's tricky, but the answer is no, because if you remember, I said that forces that make up an action-reaction pair do not act on the same object. These two forces act on the same object, okay? So be very careful. If you examine, I'm examining the forces on the puck, okay? If you ask me what are the forces on the ice, okay, well, for every action, there's an equal opposite reaction. So that normal force that I drew up there on the puck, yeah, there's a push that the ice exerts on the puck, but in turn, the puck exerts a push down on the ice, right? And so I would say that there's a kind of reaction there. And that would be this one, okay? This is the reaction to that, right? And this force I drew, gravity, well, if you look at the Earth, it's being pulled by that puck, and you would say there's that gravity pointing towards that puck, right? So this is the reaction to that one, okay? So be careful. Action-reaction forces don't act on the same object. I mean, it is true that the normal force is the same strength as gravity in our example of the forces acting on the puck. Yes, same, and they're pointing in opposite directions. Yes, but they do not form an action-reaction pair. That's the tricky part. Okay. So if someone asks, gravity is pushing the puck down. I would say gravity is pulling the puck downward towards its center. Wouldn't the ice be pushing the puck? Yeah, the ice is pushing up. That's the normal force. But these forces do not constitute an action-reaction pair, because if you look at gravity, the Earth pulls on the puck in turn pulls on the Earth. Those are the action-reaction forces there for gravity that I've encircled. Okay, that push that the ice exerts up against the puck, well, the puck exerts a push down on the ice, and so you see the normal forces there. There's also gravity acting on the ice, the sheet of ice, and there might be some other forces acting on the sheet of ice from the hockey rink, okay, but I'm not looking at that. Okay. The question: what is the reaction to the normal force pushing the puck up? So the reaction is this force here, where I drew ice. Let me put an asterisk next to it. This is the reaction to that force there. Okay. The ice pushes up on the puck. The puck in turn, or if you want, the puck pushes down on the ice, right? That's this normal force downward on the ice. The ice in turn pushes back up on the puck. There's both a gravity and normal force pushing the puck down. No. No, okay, so let me try to. Can all of you see the writing there in the middle?
Yeah, it's small. Well, I
Okay.
can zoom in. Yeah.
No, okay. So there's a question. The question is there both a gravity and normal force pushing the puck down? No. So on the puck, there's just one force acting down. That's Earth's gravity, okay? And there's one force acting up, that's the normal force. That prevents the puck from falling through the ice. In fact, if you're standing on the floor, right, of a building, the forces acting on you would be the normal force from the floor pushing up against you and Earth's gravity pulling you down. But those two forces are not constituting an action-reaction pair in accordance with Newton's third law. The reason why I'm able to sense my own weight when I'm standing is because the floor pushes up the normal force. That's what I sense. If the floor gave way, The only force acting on me is gravity. I'm in free fall, right? I don't feel a push up against me. So I would say I'm weightless as I'm falling. I mean, I have mass, okay? I don't feel my weight, but gravity is still pulling on me. So I would say I feel weightless, but there is still that pull. I still have a weight, but I can't sense it. It's called apparent weightlessness. It's weightlessness apparent to me. It's real to me, but there is actually a weight, so there's a pull of gravity. So what I'm trying to say is, I don't mean to like belabor this, but so I stand on a puck is on the ice, gravity pulls down, the puck is pushed back up by the floor of the ice, right? The ice sheet. Those are not an action-reaction pair because, for one, they act on the same object, okay? Also, if you look at the gravitational force, Earth pulls on the puck, that's what I call gravity. In turn, the puck pulls on the Earth, right? With the same strength force in the opposite direction. So that reaction is here, okay? And also, you can say that the normal force is the force that the sheet of ice exerts on the puck. But in turn, the puck exerts a normal force on the sheet of ice opposite in direction equal magnetic. And that's the reaction that I put an asterisk next to, okay? So while it is the case that on the puck, you have those two forces, gravity and the normal force, and they have the same magnitude and the point in the opposite direction, they do not form an action-reaction pair. Okay, all right, so then, good. So now, what if we do this, right? Let's say we have the hockey puck, it's on ice, okay? And I come along and I exert a push 5 newtons in strength, and you exert a push in from the opposite direction pointing leftward on west, 3 newtons in strength. And we still have the normal force, let me just call it Fn for normal force, okay? And we still have the gravitational force, let me just call it Fg for gravity, the earth pulling on it, okay? They balance each other out because there's not going to be any up-down motion. But then I want to ask you this, is there a net force on the hockey puck here in this instance? Is there a net force? There is a net force, right? There's an unbalanced force. There's a net force of 2 newtons going to the right, right? The difference between the larger force and the smaller force in the direction of the larger force. Because there is this net force, the hockey puck will move, okay? If it wasn't already moving, it will move. If you came along and you exerted 5 newtons one way, and I will have exerted 5 newtons the other way, okay? 5 and 5 in opposite direction. Technically speaking, no net force of the object should still stay at rest, right? Should just remain at rest. Friction is a force, but in this case, because I'm dealing with a sheet of ice, it's smooth. Friction is due to the roughness of surfaces when they're in contact with each other, because if you look at the underside of a hockey puck, it's not really smooth. It's like hilly, okay? And if you look at the top of that sheet of ice, it's also like hilly, right? And so like there are these hilltops and valleys and so on. So when you try to slide the puck against the ice, a valley for one surface will hit up against a hilltop of another surface, right? And then you're going to have some kind of resistance to the motion, some kind of impedance, right? And that's what friction is, right? When you have these like parts of a surface hitting against each other, trying to slip past each other, okay? It's a bit more involved than that. But at this level, I think it's okay. I'm just saying that if these surfaces were completely smooth like so, right? For the puck and the ice, then they just slip right past over each other, right? But it could be the case that if I apply 5 newtons on a puck, right, it may not yet be moving because there could be a force of friction in the opposite sense to counter me, right? And that's an issue. But let's not worry about friction right now, okay? When you have smooth surfaces in contact with each other, you can neglect friction. If there's roughness in a surface and it's fairly significant, then friction should be considered, okay? You need friction to grip anything, like to grip this stylus. There's friction between like the surface of my fingers and the surface of this stylus, right? So there's irregularity in the surfaces, they're not smooth. I'm gripping this because of friction. when you walk across the floor, there's friction between the bottom of your shoe and the pavement of the sidewalk, okay? So friction is there it has to be there whenever there's like a gripping involved, whenever there's traction, okay? Like if you're turning the head of a screw with a screwdriver, there's friction there. When you hold the door open, there's contact between the edge of the door and the hinges, okay? There's friction there. You run your nails across the chalkboard, there's friction there. Yes, if there was no friction, how would you then grip anything, right? Because things would just slip right across, right? You can keep warm with friction if you take your hands and you rub them together vigorously, right? Let's say out in the cold, if you're out there, you can heat yourself up, right? There's skin against skin. These surfaces of my hand, my palms are irregular. They rub up against each other, and friction then manifests itself as thermal energy, as heat, okay? So we'll talk about friction in some detail, but not too much, I think. All right. So there's a corollary to the statement that I just made concerning Newton's first law. The corollary is to say that an object moving at a certain speed along a certain direction will maintain this motion unless acted upon by an unbalanced or net force, okay? So the idea is kind of interesting. If you imagine being in deep outer space, far away from the pull of any planet or star, okay? And you have in your pocket, let's say, a hockey puck, right? And let's say you take the hockey puck and you launch it, right? So it leaves your hand along some direction with some speed. So there's some initial velocity, right? So let's say 20 meters per second, 30 degrees north of east, okay? That hockey puck will just coast along a straight line, okay, maintaining that speed all throughout. The velocity is kept up. Both the speed and direction do not change. It will keep going at the same speed that it left your hand with in the same direction. It'll just coast along with, there's no acceleration. No. Now, if I do that near the Earth's surface, if I take a hockey puck and I just launch it at 20 meters per second, 30 degrees north of east, it doesn't leave my hand and go along a straight line at that angle with that speed. It deflects downward, right? And its speed changes. Do you know why? Because you have a net force. What's the net force acting there?
Earth gravity.
Earth's gravitational force. Neglecting air resistance, it's just the gravitational force of the Earth. That's correct, okay? So what's kind of cool about this corollary is that for an object to keep moving, to just keep moving, no net force is required, right? For an object to keep moving, no net force is, it just can move based on its own natural tendency. Once you've begun the motion for an object, okay, it wants to maintain that motion. Now, if there are frictional forces or other forces that come into play, then the object's motion will alter, will change, right? So like, let's say, you can try this at home, right? Take a box on the floor, right? Empty it out. Kick the box, okay? You kick the box, it leaves your foot with some speed along some direction. You'll notice it'll slide across the floor and then come to a stop. So it's slowing down, right? Its speed is changing. So there must be a net force acting on it. That, in that case, the force is friction. It's the force between the floor and the bottom side of the box. There's a force that the floor exerts on the bottom side. That's what you call friction, okay? That's based on the irregularities in the surfaces that are in contact with each other. There is a net force there. But if there weren't, that box would coast along like a hockey puck on ice, just coast along with the same speed and direction of travel that a puck would have after leaving a hockey stick. Okay. So it is true, for motion to begin, listen carefully, for motion to begin, a net force is required. Okay. For motion to begin, a net force is required. For motion to continue, to be sustained, a net force is not required. And that wasn't always understood, right? That things have their own natural tendency of doing things. Now, these two statements I made can be summed up with one overarching statement. Where can I put that? Okay, let me clear the page. Right. What technically, what's the end time for us? I just need to make sure. I want to keep you okay. All right. I'll figure it out. All right. So here, going back to Newton's first law. Okay. In a way, I can sum up things by the following statement. So long, okay, so long as there is no net force acting on an object, net force acting on an object, the object will continue to do what it was already doing. In that, if an object were initially at rest, it will stay at rest. Okay, it will stay at rest. Or, okay, if an object were initially moving with a certain speed along a certain direction, it will continue to move with that same speed and direction of travel. Same speed along the same direction, okay? But again, that's only so long as there's no net force acting on the body. It basically depends on the initial state of motion. If in the initial state of motion there is no motion, then the object will continue to just be at rest if there's no net force acting, right? If initially there is speed and direction, there is a velocity, right? Non-zero velocity, then the object will maintain that velocity so long as there's no net force acting, okay? Really, both ideas have to do with no acceleration, right? So non-acceleration, right? Non-acceleration could mean that the velocity is zero always, okay? Because you're just standing still, okay? And or it could mean that, I mean, there is a non-zero velocity, like maybe 12 or something, and it's constant, okay? But the direction is also constant. I should say the vector is a constant vector, okay? Same direction, same magnitude. So that means uniform motion, uniform velocity, constant velocity. Technically, having a zero velocity means uniform velocity as well, but here I mean non-zero, okay? Both cases, there's no acceleration. The acceleration is zero, okay? So Newton's first law is really a statement of what happens with zero acceleration, right? Now we find that an object having more and more mass is better and better able to retain its current state of motion, whatever it is. If it's not moving, or moving with some speed along some direction. The more mass an object has, the better able it is to retain its initial state of motion. So for example, if I have two boxes on the floor, neglect friction, okay, two boxes on the floor, identical boxes, but in one box I place a very heavy cat, okay? And in the other box I place a teeny tiny mouse, okay? So let's say the cat's name is Tom and the mouse's name is Jerry, right? And I apply the same force on each box, same magnitude, same strength, the same force. Which is better able to retain its current state of motion, meaning being at rest? The box with the cat or the box with the mouse?
The cat.
The cat, right? The box with the cat, right? So there's more resistance to the change in motion I'm trying to bring about for the box with the cat than for the box with the mouse, right? So also, let's say, right, as another example, yeah, let's say there's a sheet of ice and it happens to be the case that there are two hockey pucks moving along the sheet of ice, okay? They're both moving at the same speed along the same direction, two hockey pucks, but let's call them A and B. But one of the hockey pucks, let's say puck A, is much more massive than the other one, puck B, okay? Both are moving in the same direction with the same speed, but one puck is heavier than the other. Puck A is heavier than the other. Now, let's say at the same time, a force is applied on each puck, the same strength force, the same magnitude force, the same force vector on each. Under the same force, which of these hockey pucks is better able to retain its current state of motion, meaning moving at that particular direction with that speed? The one that's heavier, right? Puck A. The heavier the puck, the better able the puck is or the object is to retain its initial state of motion, whatever it is, okay? So we say that in the language of physics, we say the resistance to change in motion is called inertia. A measure of resistance to change in motion in physics is just known as inertia. But for us, you can just think of this as mass. Okay, inertia is not exactly mass, it's proportional to it. But for us, it's good enough. Okay, at this level, it's good enough. And the idea is that the more inertia something has, the more mass something embodies, right? The better able it is to resist a change in motion that you're trying to bring about for it, okay? The more inertia something has, the better able it is to retain its current state of motion, whatever that happens to be, and thereby resist, better able to resist a change in motion you're trying to bring about for the body, right? That's the idea, that's the logic. And this word inertia in regular speak means resistance. I mean, if you say it in the context of, let's say, the following sentence, the senator in Congress wanted to pass a bill on climate change that was met with a lot of inertia by his peers, right? By other senators, so meaning met with resistance. The word inert itself, the prefix inert, means motionless, sluggish, okay? So that's why this first law is called the law of inertia, okay? The law of inertia. The more inertia something has, the better able it is to retain its current state of motion. If not moving, to stay not moving. If moving with a certain speed along a certain direction, to stay with that motion. Okay. There's an interesting consequence here, okay, that I'm going to talk to you about, and then I'll end class. Okay, but I'm not going to test you on it. Do you have any questions thus far? No. Okay. So in relativity theory, a theory of space and time, I told you that a passing beam of light will always be measured to have the same speed no matter what the state of motion is for the observer. Another idea in relativity theory, right, is that one cannot tell the difference between being in a state of rest, meaning not moving, okay, or moving uniformly, okay, with a constant velocity. But you cannot tell the difference unless, okay, there is an external bias. Okay, I'll explain. Now, if a frame of reference is not accelerating, in physics, we say a non-accelerating frame of reference, like let's say a stationary train or a train moving with a uniform velocity. If you have a non-accelerating frame of reference, okay, it could be because the frame of reference is completely at rest, okay, or moving uniformly. In either case, it's not accelerating, but the language that we use is also to say that it's an inertial frame of reference. We use that language. So when you hear that, it means inertial frame of reference. Or inertial means non-accelerating, okay? And the idea is that across different inertial frames of reference, you cannot tell the difference between one or the other. The laws of physics are the same, okay? Unless there's some bias that can sway things, an external bias, not internal. I'll explain, okay? So just listen, okay? I'm not gonna write this, so just listen to me and tell me what you think. Now, this is not my own example, okay? I've taken this from others who have taught me in the past. So let's say, all right, you're in a train station and you board a train because you're wanting to go to a very exotic place, let's say New Jersey, right? So you hop onto this train, you look out the window of the train, you see the pillars, a newsstand, people walking by, you see the platform, the train has not yet moved, okay? The train is not moving. The pillars are not moving relative to you. Inside the train, you find the table with refreshments on there. Like you see cups of coffee, you see donuts, okay? And so you have a cup of coffee and you take a bite into a donut, right? Until you're satiated. And then you move along, you move away from this refreshment stand and you find on the floor of the train somewhere juggling pins, right? So you find these juggling pins, and as luck would have it, when you were a kid, you were an expert juggler. So you take the juggling pins, you toss them up, they come back down, you catch them, right? You have a certain awareness, a certain kind of consciousness of what's going on, right? You're juggling these pins. They rise to maximum height, they come back down, so you get tired of doing this after all, you put the pins down, keep navigating the terrain within the train, and you find somewhere else on the train is a billiards table, a pool table, right? So you see on the table the cue ball, the white ball, you see the 8 ball, okay? And you have a cue stick, so you hit the cue ball with the cue stick center to center, and you find that the cue ball moves along a straight line path, although it's rolling, but it's moving along a straight line path, right? And it hits the 8 ball sinks it into a corner pocket. You get tired of playing the game of pool. You have a backpack with you. You take out a book from your backpack and you place the book gently on the floor of the train and just stays there, okay? You get tired of doing all these things. You go go to your seat, you sit down and you lean against the back of the chair, right? Then at some point you fall asleep. Now, this is where the interesting stuff happens. You fall asleep. As you're asleep, the blinds are drawn over the train windows. So imagine that curtains are drawn over the windows of the train, okay? Furthermore, the conductor of the train accelerates the train to a speed of 50 miles per hour and leaves it at that speed, okay? So the speed is now constant. The velocity is constant, let's say. You're 50 miles per hour east or something, right? And then you wake up. You wake up. Now you can't see through the windows because there's a curtain over each window, and you're not willing to pull up the curtains, or you can't do it, let's say. Then you see the refreshment stand, right? So you go again for a cup of coffee, for some donuts. You see the pins again, you juggle the pins as you did before, right? You see the game of pool, you play pool, you see the trajectories are straight lines if you hit center to center, right? The stick with the center of the ball. You place a book on the floor of the train, it just stays there, right? You sit down on the seat, nothing feels different than before. Your awareness of what's going on is the same as before you fell asleep, right? Your awareness is the same. The way things appear, the way things feel is the same. Right? And now an elderly woman comes to you and says, is the train moving? Is the train moving? You're tempted to say, no, it's not moving, because the things feel the same as before before you fell asleep. But the train is moving. It's just moving uniformly, but you can't tell. Now, if the windows were open and you could see trees rushing by, you have good reason to believe that the trees are not moving and you're moving in the forward manner, and it seems as though the trees are moving in the opposite sense, right? So then that's the external bias. If you have the windows open, you could tell if you're moving. But it turns out that you cannot tell the difference between being in a state of rest when the train was not moving, or being in a state of uniform motion when the train is moving uniformly at 50 meters per second or miles per hour, unless you have that external bias. The laws of physics are the same. There are no detectable changes for observers in uniform relative motion, right? Whenever there's a non-accelerating frame of reference, right, that will not produce detectable changes. But an accelerating frame of reference will produce detectable changes. You can feel and see the effects of accelerated motion. For example, let's say while the train was accelerating to 50, you were awake, you happened to be awake. If you're awake, you would feel pressed against the back of your seat. That's one thing, you would feel that. That's a direct effect, right? So you know that the train is accelerating. If you place a book on the floor of the train, that book will slide backwards. It will slide in the opposite direction. So you now know that the train is accelerating. Okay. Furthermore, when you juggle the pins on an accelerating train, that's interesting. If you throw up a pin, the pin carries the motion of the train with it at that moment. So do you. But now the pin is in the air carrying that sideways motion of the train, but you're accelerating because you're with the train affixed to the floor of it. So you move a little bit to the left, and the sideways motion of the juggling pin has not changed. So when the pin comes back down, you have to put your hand out this way to catch the pin on its way back to returning to your hand. You didn't have to do that before when the train was moving uniformly or not moving at all, right? When you hit a cue ball with a cue stick to the center to center on an accelerating train, it turns out that the cue ball will curve. It will curve, right? So you know that the train has to be accelerated motion produces detectable changes, but not uniform motion or no motion whatsoever. Okay. We say that the laws of physics are the same for observers in uniform relative motion. Like imagine you're on a platform seeing the train whiz by, but the train is moving at a uniform velocity. Me or you, the laws of physics will be the same. Things may not look the same, okay, but the laws of physics will be the same for all inertial frames of reference. They will. So for example, I might have mentioned this too. If I'm on a moving train, the train is moving uniformly, constant speed. If I take a ball and I drop it, to me it goes straight down. Okay. But if you're looking from outside of the train through a window, you're an inertial observer as well because you're not accelerating. You would say that once I let go of the ball is carrying the motion of the train with it. So you would say initially that ball has a velocity to the left, forward. So the ball doesn't drop down relative to you. You would see the ball curve down like that. It looks different, but the laws are the same. At the end of the day, it's the same force acting on the object. It's a force of gravity. Okay? So things may not look the same, but the laws of physics are the same. And it turns out also that across inertial frames, the speed of light is constant. So if I'm in the train, and I have a laser point and I shine it to the front of the train, right? Then I would measure the speed c. And if you're at the platform, you're seeing the train move, right? And you're seeing the light beam, you would expect the speed of the light beam would be c plus the motion of the train, c plus 50 miles per hour, or whatever, meters per second. But it's not. It's the same speed. Remember, all observers measure the same speed. So that's interesting, right? But you see, the reason why maybe the speed of light is absolute is that because if it weren't, right, then you could tell the difference between one inertial frame and another. You can tell the difference between being in a state of at rest or moving uniformly. Think about it. When the train was at rest, right? Before you fell asleep, if you took a laser pointer and you had shown it onto like the front, you would measure the speed c, okay? When the train is moving uniformly after you awaken, it would still be the same speed. Let me think about it. It would still be the same speed c. If it were not, right? If that speed of light were different, then you could tell now that you're moving when you weren't moving before. So it's like a big conspiracy theory, in that the speed of light is fixed in order for you not to know that you're moving, right? To keep you ignorant, to keep you thinking that you're at rest, right? Because if the speed of light changed, then you would know that there's a breaking in the symmetry, that you're now moving when you weren't moving before, albeit moving uniformly. But it's all there to hide the fact that you cannot tell if you're moving uniformly or not moving at all. Again, unless there's some external bias. All right. Any comments, questions about that? Well, later we'll see that also if you're in an accelerating frame of reference, okay, and you have no external bias, like you can't see out the outside world, if you're in an accelerating frame of reference, that the thing is the laws of physics are the same if you're in such a frame of reference or if you're in a uniform gravitational field, that you cannot draw the distinction unless there's some external bias. Like, so to give you an example, okay, just quickly, and then I'll wrap up. Let's say there's an elevator, okay, on the earth, okay. Let's say this is at the lobby of a building, okay, on the first floor of a building. You're in the elevator, but the elevator is closed off, okay. You drop an apple, right? The apple falls at the rate g. What was the value of g? Do you remember? It was like 9.8 meters per second squared, right? 10 meters per second squared. Now let's say you fall asleep, okay? And somehow some strong individual takes this elevator with you and the apple in it and puts rockets on the side, okay, of the elevator, and takes this elevator with the rockets on the side to deep outer space, okay, far away from the earth. And the rockets expel gases, and by Newton's third law, there's a reaction, there's propulsion. Let's say the rate at which the gas is being produced, or the rate at which fuel is being burned to produce the gas, gives a rate of change of speed, an acceleration this way, okay, that's equal to g, okay? So the same number, 9.8 meters per second squared. Then you wake up, okay? You wake up, you take the apple, you let go, you drop it, you measure that it's accelerating at the same rate g. So you can't tell the difference between being in a uniform gravitational field, like being near the Earth's surface, right? Where the gravitational field is uniform, it's not changing with distance, okay? Or being in an accelerated frame of reference without there being any gravitational field whatsoever. The physics is the same. So that's saying something about gravity, that you could mimic gravity. There's more to say about this, but this idea here is the content of Einstein's general theory of relativity, okay, or general relativity. One's called the special theory of relativity, the other is called the general. Of course, the general theory is more general than the special theory. Okay. All right. Special theory of relativity deals with space and time. The general theory deals with gravity, the nature of gravity. Let me stop there. All right, I'm going to stop recording.